crack relativity step 1. Well, we cover probably 80% of special relativity in step 1. Step 2, we cover the remaining, and step 3, we cover the basic part of the general theory of relativity. So 3 steps, you will understand everything about the Einstein relativity theory. Okay, it's a very aggressive video, but if you like, you can watch again and follow up. The relativity is pretty much what it is the coordinate transformations. And suppose you have a car A, and inside the car you have a clock, whatever, those items expressed by x1 and time clock t1. And you have another car B. Inside the car has another clock and some various items. Those are expressed by coordinate x2 and t2. Okay, so what has been changed in the relativity from the classical physics means newtons, is okay, when the car B is moving at the speed v, okay, the newtons, it doesn't matter you use this coordinate or this coordinate, because the x1 is going to be x2 plus bt t1, because say you have a clock here in this coordinate x2, okay, the x1 is all the way here, so vt, it's moving at the speed v. Simply you can convert the coordinate. And the other way around, if we use this coordinate, something here that's x1, then what we do is x2 equal the x1 minus vt. So that's a simple coordinate transformation. The Newton's assumption, number 1, t is universal, means clock is ticking for everybody at the same rate. So use t1 or t2, doesn't matter. Okay, and the absolute reference point, that means somewhere in the space you have one place that the origin, so you can tell who is moving. The car B is moving at the B, the car A is staying there without moving. That's all you can tell by origin. And you ask Newton, where's this origin in the space? He said, I don't know, but there must be somewhere, because we know who is moving and who is not moving. Okay, this is a questionable, very vague assumption. Well, Lorentz, before Einstein, the Lorentz assumed there's no such a thing like origin. The car A thinks B is moving at the V. The car B thinks car A is moving this direction at the V. You cannot tell who is correct. So this idea of relativity came up. Okay, so if Newton's assumption, two assumptions is correct, this transformation is correct. But Lorentz tried to do different transformation. Okay, these assumptions are not correct, and T is not universal. This is added later because that time there are experimental fact that the light speed seem to be constant by any observer. For example, A is going at the V and emit the light, and B receive it. So is this light speed V plus light speed C? No, it turned out to be C. It's very strange. For every observer, the light speed is constant. Okay, that was an experimental result that at that time. So the Lorentz tried to take care of this, and in order to take care of this, T has to be independent from coordinate 1 and coordinate 2. This is called frame. This observer in car A is frame A, and this called frame B. Okay, so he successfully did this coordinate conversion so that everybody equal footing. A thinks B is moving, but B thinks A is moving. It's not like Newton say, hey, I know who is moving. You are not moving, and this guy is moving because I have an absolute reference point. No, without absolute reference point, he wanted to do coordinate transformation and also taking care of this. There is a maximum speed. Okay, so these are the requirements for Lorentz transformation. Now, in order to do that, he introduced very convenient factor. Now it's called relativity factor. Okay, this factor comes into the coordinate transformation. What it is if V is much smaller than maximum speed C, then this is going to be 0. So lambda will be nearly 1. Okay, if lambda is nearly 1, then what we observe, this is going to be true. This classical physics result is true. If V goes close to C, then lambda would be bigger than 1. Okay, then I think this Lorentz transformation still works for that case. Okay, so he came up with this. Actually, this is only one you need to know about special relativity. Here's a lambda. So frame 2, see what happened is when two cars going, okay, this frame A live in a different world than the B. He has coordinate and time, and he suppose he cannot see the B. Okay, frame A can see only on monitor what's going on within the B. And within the B, everything expressed by x2 and t2 coordinate. So the x2 and t2 coordinate are shown on the screen monitor. That's what KA's monitor is about. Okay, so the frame A has x1 and t1 in his world. Here's a clock, that x1, and anything else inside frame B is going to be shown on the monitor. And in the monitor, the actual all the coordinate and time is calculated from t1 and x1. Okay, so in this equation you have to understand the meaning. Okay, the t1 is frame A's clock. Okay, and here x1 is when the B started leave. Initially had x1, that's the distance. Okay, so actually if you calculate t1 and x1 from this equation, you get this. So completely opposite result. Now B has monitor and B has his own world using t2 x2. Now he wants to know what's going on in the frame A. He sees the monitor, so he see what's going on here. So this is the coordinate transformation. That means in this equation, all the coordinate in the B is calculated from these coordinate in the frame A, and opposite is true. Okay, and this is all you need to know. The relativity. Okay, so there are two kinds of relativity. It's called special and general. Okay, what's a special relativity? Special relativity handle only for inertia system, means moving at the constant B, constant. Okay, then we have a frame A, frame B, and coordinate conversion is done by this. Okay, the general relativity handle acceleration and gravity, and those since acceleration is, the force, and the source of force is gravity, so they are all in the complete theory. Okay, and general relativity need a little bit higher grade math, but we get into the basic part of the general relativity in the step 3. Okay, so inertia system means something moving at a constant speed that we can handle by special relativity, and this is all you need to know. This tells you everything about what's going on in this world. Okay, and as I said, when v is small, much smaller than maximum speed, then factor become 1, and this turned out to be t1 become t2 become t1, and x2 become x1 minus t1b. So it's become like classic Newton's equation. So when speed go faster, close to light speed, then it's deviate from classical Newton's equation and have a relativity factor comes in. Okay, this relativity factor has a lot of things in it. So for example, take this equation, right? And for simplicity, we consider this is 0, means B start moving at the same location as A at the speed v. Okay, so we have an equation t2 equals lambda t1, and the lambda is larger than 1. Now think carefully. Okay, when something happen, this is t1 is the frame A world, and t2 is the frame B world. Okay, so something happened inside the B. It took t2 times, say 3 seconds. Okay, and now we assume lambda is 1.5. Okay, so what happened is, then for t1 it's going to take only 2 seconds. So something took 3 seconds. The event on the B is actually, it's a 2-second event in frame A. Okay, what does it mean? So which clock is ticking faster, frame B or frame A? Well, we have to phrase the question this way. Suppose you have one job to do, and the guy took 3 days, another guy took 2 days. Who is slow? 3 days, right? Okay, so this guy, the world is moving slower, because for frame A, observer in the frame A, see this guy takes 3 seconds. We're all talking about this part, so it's we're talking about the observer A. But observer A, his clock, it's only 2-second event. So why the frame B event in the frame B is taking 3 seconds? Because it's event is going slower. Okay, this is, I know this is confusing, but you have to understand this. Okay, so it's applied to this. If you look at this equation, it's symmetric, right? So from B, he observed A in the monitor and measured the event. They say, oh, it's going slow. It's taking 3 seconds. But here, the same event is 2 seconds. So the thing's moving slower. So B thinks A is moving backward. So everything's going slower in A. But A thinks B is moving at the B. Everything inside the B is proceeding slower. This is called time dilation. So what happened is time is stretched. Anything inertial frame, anything moving at the speed v, the things seem to be going slower for the observer on the other side. Okay, the observer within the B doesn't think so. He thinks time goes as normal. But for the observer A, the B thinks going slower. Okay, and same thing, the B thinks everything in A, in the monitor he watch, going slower. But A doesn't think so. A has a time t1 and it's ticking normal. But for B, he observed A, it seemed to be going slower. Okay, that's the time dilation. It goes both ways. So once time dilate, what happened to the simultaneity? The events is never be simultaneous for observer A and B, because event happening A, B see slightly late. So the other way around too. Any event happen in B, the A see slightly late. Okay, so they never see the event at the same time. Well, it's not fair to say they don't see at the same time. The problem is you cannot compare the timing, because this guy has his own time, this guy has own time clock, and simultaneously is correct within frame B, within frame A, but between A and B you cannot say anything about simultaneous, because depend on who observe who. Okay, so once simultaneity is confined within a frame, same word. How about causality? Causality is cause and effect, right? So cause is always happen earlier than effect. But what's happened if cause in B and the result come to A, then cause show up on the monitor later? Is that a violation of causality? Not really. This monitor is whatever the cause in B, it's not cause in A. So effect is A. For example, you shoot a light and the light reach to the A, that's effect. But the shooting, switching the flashlight is a cause, is displayed on monitor late. So you have a light arrive first before the flashlight switch on. Is that a violation of cause and effect? No, because this cause is within a frame B, not A. Okay, so causality also confined within a frame. And how about maximum speed? There's a maximum speed. So people misunderstand special relativity is all about light speed. No, it's all about maximum speed. And light happen to go at the maximum speed, and there are a few others, the particle go at the maximum speed. It's not about the light, it's about maximum speed. Okay, and contraction of length. Well, go back to that equation, basic equation here. Okay, now 1 meter length in frame A is going to be, and the lambda is larger than 1. On the monitor it doesn't look like 1 meter, it's a little bit shorter. Okay, so anything moving frame, moving at the speed v, seem to shorten the length. That's called contraction of length. Okay, so we're covering everything in a short time, so you have to follow up by your own research later. Twins paradox. Suppose the twin brother A stay on Earth. The B goes to the space trip, right? And it's moving, so for A, B is going slower, right? And B come back, still moving at the V. So for A, the B thinks, oh, A gained aged, and the B still young. And then but the relativity theory also said B thinks A is young, B is gaining, the B is aged, and A is young. That's what A see, but B observe, but A observe this way, totally opposite. How do you reconcile this? This is called twins paradox. Okay, so I give you the answer first. When B change the direction, it's need to deaccelerate and turn around and accelerate. Okay, during this time B is receiving force, so it's not inertia system anymore. We have to bring in general theory of relativity. When you receive the force, clock slow down. So what's happened to B? B thinks he's aged, but because it's slow down clock, it catch up, right? So what's happened is now B is younger and A becomes aged more than B, and when he come back to Earth, here you go, there will be no contradiction. Okay, that's what twins paradox is about. Okay, so that's the end of this video. It's getting long, and I hope you like it. If you like it, please check step 2 and subscribe.